Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon, but it's kind of got to make you laugh to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. Everything in our world is perfect, there are models all over the world. But despite years of research, some mysteries remain unsolved. Why does time flow in one direction? What's the truth behind gravity? Why does time slow down when we travel at the speed of light? This question has fascinated us for thousands of years. What if I told you that gravity is a lie, created solely by the human brain? It may seem incredible, but that's what the famous Dr. Brian Cox recently claimed. To understand the nature of gravity and why time is slow, we must go beyond Newton. The problem is not what he understands, but what he cannot do. One of the problems with Newton's theory of gravity is that it only allows us to predict how objects will move under its own force. It doesn't explain why gravity exists or even how it works. It just makes you count, and Newton knew that. In fact, it is said that the most beautiful things, the sun, planets, and comets, work only according to the rules and instructions of the sages. In other words, Newton provided the tools to understand how things move but didn't explain how or why, leaving that up to God. There are many mysteries waiting for us to discover in the vast universe around us. Among these mysteries are some incredible phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time is strange, where it could be slower or faster, where the forces that keep us grounded would not be like them. This is the area where Albert Einstein's theory of relativity and our understanding of time and gravity become different. The famous Albert Einstein, whose theory of relativity gave us a new way of thinking about the world, underpins our understanding of how time behaves in different situations, especially when we travel at high speeds. It all started in the early 20th century when Einstein proposed two important ideas, special relativity and general relativity. The theory of special relativity, published in 1905, changed our understanding of time and space. It basically tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. The theory introduced the concept of social interaction, including the famous theory that time expands or slows down in certain situations. One of the best ideas used to explain time dilation is the light clock. Imagine things in a spacecraft moving at incredible speed, close to the speed of light. In the spacecraft, a beam of light is reflected on two mirrors perpendicular to the direction of motion. To a plane observer, light travels in a straight line by bouncing vertically. However, for an outside observer who is not moving with the plane, the situation looks different. They see the plane moving at high speed and follow the path of the beam. Because the plane is moving, the beam must travel farther to hit the mirror. According to the laws of physics, the speed of light is constant for all observers. Therefore, the beam should look like a long diagonal path. Now things get interesting. The time it takes for the rate of travel must be the same for observers inside and outside the plane. However, since the path to the external observer is longer, the light takes more time to complete its journey. The apparent time difference between two observers is what Einstein called time dilation. Time delays for the observer moving towards the stationary observer, so in this case, the timing differs depending on your actions. This isn't just an idea, these experiments confirm the social impact. For example, particles in particle accelerators such as the Large Hadron Collider can reach speeds close to the speed of light. In order to make accurate measurements, researchers must take into account the effects of time dilation. Special relativity opens the door to a world where time is infinite and can be stretched or compressed according to your power. It challenges our everyday thinking and makes us realize that the universe works far beyond our experience. Einstein's theory of special relativity, proposed in 1905, transformed our understanding of the structure of the universe, especially time and motion. Critical theory shows that the laws of physics apply equally to all non-accelerating observers, regardless of their motion. To better understand special relativity, let's examine its basic elements. One of the fundamental concepts of special relativity is that the speed of light is the same for everyone, regardless of motion. Whether you are stationary or moving fast, light always appears to be moving at the same speed, which is approximately 299,792,458 meters per second. This idea contrasts with our everyday experience that when we move, our speed generally increases. Apparently, the universe has a speed limit, and that speed is the speed of light. According to special relativity, we believe that events that occur at the same time do not occur at the same time for everyone. If two events are happening in different places and you are moving towards those events, what you see happening at the same time will not happen to someone else at the same time from a different perspective. This seemingly strange concept challenges our concept of time. The concept of time dilation is one of the most important and useful theories. As mentioned in the previous section, time will slow down or lengthen as you move. The faster you move, the slower time appears to pass for you relative to a stationary observer. This effect becomes even more pronounced when you reach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at speeds close to the speed of light. When the twins return, the one who traveled will be younger than their sibling on Earth. This phenomenon, often called the twin paradox, is a phenomenon of real-time dilation. The reason for this difference is the constancy of the speed of light. As the twins walk towards it with quick steps, the ticking of the clock seems normal to them. But to Earth observers, the spacefaring twins' clock appears to be slowing down as the twins travel to different parts of the world. Another consequence of special relativity is length contraction. When an object moves at high speeds, its length in the direction of motion appears short to a stationary observer. This effect is very small at everyday speeds but becomes more pronounced when objects reach the speed of light. One of the most famous equations in physics, E = mc², is a direct consequence of the special theory of relativity. This equation shows that energy and mass are interchangeable, meaning that mass can be converted into energy and vice versa. This principle is important for understanding the high-speed behavior of material and the energy released in processes such as nuclear reactions. Special relativity is more than a theoretical concept, it has practical applications. For example, GPS systems rely on the accuracy of satellite signals. However, as the satellites move towards us, the time dilation effect comes into play. If the effects of special relativity are not taken into account in GPS calculations, the accuracy of our navigation system would decrease. Special relativity forces us to rethink our concept of time and space. It shows that the universe works in a way that resists modernity. Time is not an absolute concept, it is relative and affected by movement. The speed of light and the relationship between energy and mass are important ideas that have been confirmed by many experiments. Now let's move on to general relativity, another concept proposed by Albert Einstein in 1915. This theory takes us into the world of gravity and reveals the connection between gravity and the structure of the universe. General relativity essentially challenges the classical concept of gravity as a force acting at a distance between masses. Instead, it presents gravity as the curvature of space-time. The idea is simpler than it seems. To understand general relativity, we must think of the universe as a four-dimensional entity that combines 3 dimensions of space and 1 dimension of time. In four-dimensional spacetime, large objects like stars and planets warp the fabric of spacetime around them. This curvature is what we think of as gravity. Think of spacetime as a giant flexible model. An object as large as the Earth would create an indentation in this fabric. When you place a small object such as a ball near the Earth, it rolls into the indentation. This is similar to what happens when an object comes under the influence of gravity. It is not a mysterious power, it just follows the curvature of spacetime. General relativity provides a powerful explanation of the motion of celestial bodies in the solar system. It accurately predicts the orbits of planets, such as the elliptical path the Earth follows around the Sun. The old concept of gravity as an attractive force does not explain all orbital motion, but the concept of curved spacetime does. One of the most famous observations of general relativity occurred during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight caused by the Sun's gravity. The theory is that the Sun's massive presence bends the path of light from distant stars, causing them to appear slightly out of place. Observations during the eclipse confirmed the theory, validating Einstein's predictions. Gravity affects time just as motion affects time in special relativity. In areas of strong gravity, time passes more slowly than in areas of weak gravity. This means that if you are standing near a massive object such as a black hole, your watch will run slower than if you are standing further away from the massive object. General relativity introduced the idea of the black hole, the site of the greatest challenge to our understanding of gravity. The gravitational pull of a black hole is so strong that nothing, not even light, can escape its grasp. The boundary around a black hole is called the event horizon, and it is the point of no return. Anything that crosses this boundary will be pulled into the black hole. General relativity also has a profound impact on the structure of the entire universe. Einstein initially included a cosmological constant in his equations to keep the universe static. However, when he discovered that the universe was expanding, he described it as his biggest mistake. The expanding universe theory supported by general relativity forms the basis of the Big Bang theory, which explains the origin of the universe. Another important predictor of general relativity is the existence of gravitational waves. These are ripples in the fabric of spacetime caused by massive accelerating objects such as black holes or merging neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, confirmed another part of Einstein's theory by directly detecting gravitational waves for the first time. Over the years, countless experiments have tested general relativity, and it has always passed the test. Whether it is the actual orbits of planets, the bending of stars, or the observation of gravitational waves, this theory has been confirmed time and time again. Considering the nature of gravity in our daily lives, the idea that gravity is a lie may seem shocking, even counterintuitive. However, in the world of physics, there is always room for debate, speculation, and the search for alternative theories. It is not uncommon for scientists to challenge commonly held assumptions. There are different theories about gravity that challenge the traditional understanding of this fundamental force. Their arguments revolve around alternative theories, some of which aim to modify or replace our understanding of gravity. One of the best-known alternative theories is modified Newtonian dynamics, also known as MOND. It shows that at low acceleration, gravity behaves differently than predicted by normal Newtonian gravity. According to MOND, there is no need to appeal to dark matter to explain the behavior of galaxies. Instead, MOND proposes that gravity accelerates to very high speeds. The main points of the debate about gravity focus on dark matter and dark energy. These are mysterious ideas put forward to explain some phenomena in the universe, such as the rotation and expansion of galaxies. Critics of the traditional view of gravity argue that dark matter and dark energy are unnecessary and that other theories can explain the phenomena. Some scientists disagree that Einstein's theory of relativity is incomplete. They say there may be other important, undiscovered, or powerful forces at work that could change or improve our current understanding of gravity. These researchers are exploring many possibilities, including theories that suggest new properties or interactions. It is worth noting that alternative theories are not immediately abandoned. The scientific community rigorously tests these ideas to determine their effectiveness. Although various alternative theories have been supported so far, none are believed to change the design of gravity. It is important to emphasize that doubt and skepticism are important aspects of science in the search for knowledge. It is healthy to question established ideas and explore alternatives. Science arises from doubt and investigation. When scientific consensus is challenged, this can lead to further investigation and deeper understanding of the universe. Despite competing and alternative theories, gravity as explained by general relativity remains the most important and successful theory. That's because it constantly undergoes extensive testing and accurately describes events from Earth orbits to the bending of stars. The simplicity and comprehensiveness of general relativity make it difficult to change. As we talked about, Einstein's theory of special relativity introduced the concept of time dilation, where time behaves differently depending on your energy. Now let's examine how this theory has real and practical implications, especially in the context of destination travel. Space exploration has always attracted people's attention. We dream of exploring distant planets, stars, and even galaxies, but traveling far from Earth has significant challenges, the vastness of the Earth and the limit of the speed of light. According to Einstein's theory, The speed of light in a vacuum is the fastest speed in the universe. Nothing can move faster than the speed of light. This limitation poses a major challenge for interstellar travel because even with the most advanced technology, it takes a long time to reach the nearest star. To understand what time dilation means in space travel, let's look at the famous twins paradox. Imagine that one of the twins remains on Earth while the other departs for a distant star at a speed well below the speed of light. When the twin returns, they will find that they have spent less time on Earth than their sibling. The twin who went on a space journey went into the future. Time dilation is very useful for tourists. The longer the journey, the greater the time dilation. The time dilation effect is significant during space travel to nearby stars. This could mean that astronauts age more slowly than those on Earth. Although this may seem like the stuff of science fiction, it is actually a result of relativity theory. Imagine a future where humans send heavy missions to a nearby star. Because of the distance, travel at even a fraction of the speed of light can take decades. For the astronauts on board, the journey will feel shorter due to time dilation, but the world they leave behind will be older. Time dilation not only affects living organisms but also affects technology. For example, time dilation must be compensated for to ensure the accuracy and function of computer systems and communications equipment on board spacecraft. The fast-paced social media travel environment brings with it many challenges. People working in this way need to consider the effects of long-term isolation, exposure to cosmic radiation, and the psychological effects of being separated from Earth for long periods of time. Although space travel to distant stars is still a promising future, the effects of time dilation have already entered our daily lives. The Global Positioning System, GPS, relies on the accuracy of satellite signals to determine location. The satellites are moving relative to us and are affected by time dilation. If relativistic effects are not taken into account in GPS calculations, the accuracy of the navigation system would be greatly affected. Now let's examine the concept of why time flows in one direction. Time is a concept that directs our lives and the entire universe. It flows with decisions from the past to the present and the future. This one-way journey from past to future is the essence of our existence. So why does time have such a path? The key to understanding why time goes in one direction is a concept called entropy. Entropy is a measure of disorder or randomness in a system. It is an important concept in physics and is related to the arrow of time. Simply put, entropy increases over time, and this increase in disorder or randomness occurs over a period of time. The relationship between entropy and the direction of time is contained in the second law of thermodynamics. This law states that in an isolated system, the total entropy will always increase or remain the same overall. In other words, entropy has a natural tendency to increase and does not decrease on its own. Entropy is everywhere, and its effects are clear. For example, imagine a deck of cards arranged in perfect order. Then, if we shuffle the cards, they become out of order and random. The entropy of the ordered deck is lower, and the entropy of the shuffled deck is higher. The transition from order to chaos is the result of the arrow of time. The increase in entropy is clearly visible at the macroscopic level of our daily lives. We see this when analyzing ice melting in water or the contents of a cup of coffee mixing. This macroscopic process embodies the unidirectional flow of time. When we look at the microscopic world of atoms and particles, we see that the laws of physics are symmetrical with respect to time. This means that at the microscopic level, processes can be reversed. If you watch a video of an accident and play it backward, you won't be able to tell the difference. This phenomenon is called time reversal symmetry. The apparent contradiction between reversibility in the microscopic world and irreversibility in the macroscopic world arises from the concept of initial conditions. The macroscopic world consists of many things and their interactions. The initial conditions of this complex world give rise to the arrow of time. The idea of a unidirectional flow of time is not limited to physics and the universe. Our brains process information in a sequence from past memories to present and future expectations. The existence of time is closely related to our perception of the existence of time in the external world. The one-way nature of time also raises important questions about reality. It challenges our thinking and understanding of cause and effect. We tend to see the past as fixed and the future as full of possibilities. These physical patterns shape our worldview and judgments. The existence of time is the basis of our life. It informs our knowledge, our progress in life, and our understanding of the universe. Without time, our reality would be very different. Our actions would have no consequences, and no cause and effect would be seen. Thanks for watching another episode. While you're here, click on the video on your screen to watch more exciting videos like this.